Hello learners, welcome again to this another class on the course Digital System Design, and the topic of today's talk is code converters. We take as an example BCD to Excess-3 code converter. So let us begin. Dear learners, there are variety of codes available to represent same binary information in different ways, like BCD. Then we have Excess-3 code, which is also called self-complementary code. We have gray code, and so on. So sometimes we need to communicate from one code to another code. For that purpose, we essentially needs code converters. So in today's class, we are trying to design a code converter circuit that is called binary coded decimal number or binary coded decimal information to Excess-3. So we will take 4-bit BCD number which represents decimal number from 0 to 9, and then we will write equivalent Excess-3 code, and after that we will design a circuit which can generates equivalent Excess-3 code with respect to BCD code. So strategy is, first we will write the truth table of BCD to Excess-3 code. So let us represent this BCD number in four bits. That is, here we write BCD. These numbers are represented as A, B, C, and D, where D is least significant digit, whereas A is most significant digit. So BCD number 0, 0, 0, 0, and then corresponding Excess-3 code we will write here. Excess-3 code. We will represent this Excess-3 code with 4 letters, that is W, X, Y, and Z. So the corresponding number of Excess-3 code with respect to BCD0 is just adding 3 in the existing BCD code. So if we add 3 in 0, 0, 0, 0, so we will get 0, 0, 1, 1. That is the equivalent Excess-3 code, that as name suggests. Next number in BCD is 0, 0, 0, 1. So corresponding Excess-3 code will be 0, 1, 0, 0. And let us write here, then 2, then 3, then 4, 5, 6, 7, 8, and 9. From 0 to, I will write here the corresponding decimal number for your reference. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And now let us complete writing this Excess-3 code. So equivalent of 2 by BCD 2 is here 5. So 0, 1 is then 6, then 7, then 8, 9, 10, then 11, and lastly 12. So this is the truth table of BCD to Excess-3 code converter. Now we have to find out the expressions for output, say Z, in terms of BCD inputs. So for that purpose, we use Karnaugh map, say 4 variable Karnaugh map. I'm taking one by one. First, I will take, say, Z. So we need 4 variable Karnaugh map, which is called 4 variable K map. So since inputs are in BCD, A bar, B bar, A bar, B, A, B, A, B bar, here C bar, D bar, C bar, D, C, D, C, D bar. And let us try to write the output. So Z is here. So 1, 0, 1, 0, this 4, 1, 0, 1, 0, then 1, 0, 1, 0, 1, 0, 1, 0. So next 4. Then these two, 1, 0. This is 1, 0. And rest are don't care condition because 10 to 15 are not defined in BCD. However, 4-bit binary number goes from 0 to 15. So let us try to solve it. So we can solve. So we can see here, we can make group of 8 ones, that is the octet, like this and like this. So by folding this Karnaugh map from these two columns, so from here we can write Z is equal to, you see here, D bar. So Z is equal to D bar. So this is the first solution. Similarly, find out the second solution for this Y, X, and W. So let us do it. Okay, let us write here. Okay, I can use some drawing. This rectangle. And then line. And after that, let us try to fill up this information for Y. So you see, I am writing here 1, 0, 0, 1, then 1, 0, 0, 1, then 1 and 0. And rest are don't care condition. So now try to solve it. So from here we can see these are making group of 4 ones, that is one quad is here and another quad is here. So this is y, which can be written as y is equal to, from here we can see this is your CD and this is C bar D bar. So we can write here CD plus C bar D bar. So this is nothing but exclusive NOR of C and D. Similarly, let us try to find out the expression of X from the table. So again, let us draw this Karnaugh map of 4 variable. Then line 1, 2, then 3, then 2, and 3, and these are in terms of A bar, B bar, A bar, B, A, B, and A, B bar, C bar, D bar, C bar, D, C, D, C, D bar, and X value we have to take from here. This is the column 3. So 0, 0, 1, 1, 1. 0, 1, 1, 1. Let us write here 0, 1, 1, 1. First 4. Next is 1, 0, 0, 0. 1, 1, 0, 0, 0. And rest is 0, 1. 0, 1. And other conditions are not defined. That is why we put don't care condition. Here, in order to solve this, let us try to see how we can minimize. So first of all, we can make, in order to group this, we can make group of 4 ones like this. And one more from here to this way. So this one is remaining. I think we cannot simply further, so accept a pair. Now 2 quad and 1 pair. So from here we can see this is B bar and B bar D, B bar D, and from here B bar C, B bar C, plus this is pair from here 2 rows, so B and C bar D bar. So this is expression for X. And now let us find out the expression for W. So I will draw again a Karnaugh map. So we are trying to write the output expressions in terms of the input. So output is here Excess-3 code and input is here BCD code. So corresponding this LSB, then next higher MSB, and so on. So this is now drawing. So again, the number is mentioned here, like this W1. So 4, 1, 2, 3, 4, 5, 5 0, and then 5 ones. So let us insert. So right here, 5 zeros and 5 ones. Okay. So 1, 2, 3, 4, 5. Then 5 1 1, 2, 3, 4, 5. The rest are don't care condition for the case of W. So we will write here W. And now let us try to solve it. So we can see, can make an octet here, group of 8 ones, and two group of 4 ones, that is quad. This is 1 and this is second. So now let us write expression. So W is equal to, from here octet, you can say this is A, and from second quad, from row we are getting B, and from column we are getting D, BD, and from here again B and C. So this is the final expression. So we can write here again. So first is this W X Y Z. So Z is already mentioned here. This is called A plus BD plus BC. Then X is also mentioned here. B bar D bar plus B bar C plus B C bar D bar. And then we can write here Y. Y is mentioned CD bar. CD plus C bar D bar, which is nothing but exclusive NOR of CD. And W first, and then Z is equal to D bar. No. Actually, I wrote wrong here. This is W from here, and this is X, this is Y, and W is Z basically. W is equal to Z is equal to D bar. Z is equal to D bar W X Y and so let us see. So you got Z is equal to D bar. You got X is equal to B bar, C bar, B bar, D, B, C, D bar. Then Y is equal to CD plus C bar, D bar. And W is equal to A plus BD plus BC. So order wise, so this is W, X, Y, Z, reverse order I have written here. Now next is to realize with the help of logic gate. So in order to see the expression, it is always better to implement these things side by side so that we can You can see the diagram. So for that purpose, we need 4 input lines. So I take lines with the help of suppose this. So input is A, B, C, D. So I take A and then this will generate A bar and this will be A. Similarly, input is B, then B bar, B, then let us see, it will be C bar and here C, and then D, let us take this D bar and it will be D. So all 4 lines are available. Now we try to implement circuits. So simplest Z is equal to D bar. So D bar will give you the Z, that is the least significant of Excess-3 code. Then we have next one is the Y, this one. So Y I will implement C and D exclusive NOR. So C is here and D is here, and I will take a gate called exclusive NOR. So this will give you Y. So W actually it should have been first X. Anyway, then X. Let us take X. X is here. So X can be implemented B bar, D bar. B bar is here. Then D bar is here. And we can get this one. Then B bar C. We take here B bar and C and get. And then third one is B, which is here. C bar, D bar. The C bar is here and D bar is here. So after that we take and next is just to use 3 input OR gate to get the output of X. And then W is A, B, D plus BC. We will use here this one. So A be here, then BD, B is here, and D is here. Use AND gate, and then BC. So we have here B, and we have here C. This, after that, we can use OR gate to get W. So let us complete this one. The circuit here. This is red. Just to ensure that there is a connection, and this is connection, here connection, here connection, and this is a connection. So now we are getting all 4 outputs variable W, X, Y, Z. So input is here BCD number. Here you can say in terms of box. So this is BCD to Excess-3 code converter. So input is 1, 2, 3, 4, A, B, C, D, and outputs are W, X, Y, Z, which are Excess-3 code converters. So inside this box is the circuit, right hand side, the circuit which I have drawn. So you can count how many gates and what type of gates are there. So with this class concluded today. So what we have learned is BCD to Excess-3 code converter. So we started from the truth table. We saw that truth table expressions of W, X, Y, Z. We got the output in terms of input variables and then implemented with the help of logic gates. With this, thank you for attending this class.